All right, so this is the Euler's method lesson. So we've begun to take a look at differential equations. In the last screencast, we talked about slope fields, which were ways to visualize solutions to differential equations. Euler's method is a numerical method. It is going to be a way where we take a look at these differential equations with numerical methods. They're going to let us crunch some numbers that do some approximating. Euler's method is based on tiny pieces of tangent line. In the slope fields, these tiny pieces of tangent line litter the landscape. But in Euler's method, the tiny pieces of tangent line are the things that we ride to get from one point to another. So I'm gonna demonstrate. It's actually easier to demonstrate than it is to talk about. So to do Euler's method, you need a differential equation. And this particular differential equation is dy dx is x plus y plus 1. And you need a particular point on the curve. You have to know what the y value is at a particular x value. In this case, we're going to let x and y be 1. That's going to be a point on the solution curve. We're going to use Euler's method with two sub-intervals to approximate the y value at 1.2. So if I can, here's the idea. This is grossly not to scale. This is the point 1,1 that's on the curve. Here's 1.2. This is grossly not to scale. Two subintervals would put some rest stop over here. Here's the plan. We're going to construct the tangent line at 1,1. We're going to construct it. We're going to ride that tangent line until we get to this rest stop, wherever that is. Then we're going to reevaluate what the tangent line should look like, and then we're going to ride that piece of tangent line until we get to 1.2. And nothing we do here is going to be any more complicated than 9th grade algebra, I promise. So here's the basic idea. At 1.1, at the point 1,1, what is dy dx? X plus y plus 1. X plus y plus 1, that's 3. So we are going to construct a piece of tangent line, and its slope is 3. We're going to ride that piece of tangent line all the way to here, all the way to the point 1 where the x value is 1.1. So this distance is 0.1. Want to know what that distance is. Now, in 9th grade, we learned that slope is delta y over delta x. So the slope is the change in y over the change in x. And that means that the change in y is 0.3. This change in y is 0.3, which means that the coordinates of this point, the x coordinate's 1.1, the y coordinate started at 1 and went up by 0.3, so the y coordinate is 1.3. So this red dot, so we started at the black dot, this red dot has coordinates 1.1, 1.3. Euler's method says at this point, reevaluate. What's the deal at 1.1, 1.3? Well, the slope of the tangent line is the x value plus the y value plus 1, 1.1 plus 1.3 plus 1, that's 3.4. So we're going to draw a tiny piece of tangent line, and that tiny piece of tangent line is going to have a slope of 3.4. How do you get a slope? Well, there's a rise and a run. The run is dictated for us. The rise is what we want to know. So I learned that slope is delta y over delta x. So delta y is 0.34. Well, what does that mean? The coordinates of this point, the x-coordinate's 1.2. The y-coordinate started at 1.3, went up by this much, 1.64. So the y value at 1.2 is approximately 1.64. This is how we use Euler's method. This is how we do it. I will demonstrate with a second example. Again, to set up Euler's method, you need a differential equation. In this case, we're going to choose x minus y. And we'll let y of 1 be, I don't know, 0. And then we're going to use 2 equal subintervals to approximate. Let's make this y of 2 equal to 0. And let's approximate y of 2.4, just so it's not the same thing as before. So again, grossly not to scale. Here's 2. Here's 2.4. 2 equal subintervals dictates that. So we start here at 2, 0. And we ask ourselves, at the point 2, 0, what's dy dx? Dy dx is the x value minus the y value, that's 2. So we draw a tiny piece of tangent line whose slope is 2. We know that that tangent line creates a rise and a run. The run is pretty obvious. Want to know what the rise is. So slope is change in y over change in x. So the slope is delta y over delta x. So the change in y is 0.4. So what? Well, that means that the coordinates of this point are known. The x-coordinate is 2.2 because we rigged it that way. The y-coordinate started at 0 and went up by 0.4. It's now 0.4. So then we ask ourselves, at that new point, 2.2.4, what is dy dx? Well, dy dx is the x value minus the y value. The x value minus the y value. So we draw a tiny piece of tangent line whose slope is 1.8. And we know that the slope is delta y over delta x. Slope is delta y over delta x, which means the change in y is 0.36. Well, if the change in y is 0.36, then we know everything we need to know. The y value started at 0.4. It went up by 0.36. This is 0.76. And so the y value at 2.4 is approximately 0.76. Euler's method, a numerical way to take a look at differential equations. The thing that you should come prepared to do, suppose that dy dx is negative x over y, and the y value at 0 is 4. I want y of 1 with 2 equal subintervals. Want to know what that is? We'll talk about it when we gather, and our 10 minutes are up.